What's up, guys? Today we're talking about life contingencies. So this is where we're going to discuss the probabilities that someone is either alive or dead at some certain time, given their age. So in front of us here, we've got a life table. So this is very important. We're going to be working with this a lot. There's lots of different life tables. I've just got one here that I'm using to explain. So life table, it's like a convenient way to summarize different probability distributions that are going to be associated with someone's life, when they're expected to die, their future lifetime. So let's start here. So the X is representing their age. So we're dealing with 47, 48, 49, 50-year-olds here in this segment. So LX, the first column we've got here, is that number is the number of people that is expected to survive X years. So we expect to have 33,045, whatever number of people alive at age 47. And then DX, the next column, is the number of people that are expected to die within that many years. So in 47 years, we expect 110 point something people to die. Next column, we've got QX. QX is the probability that someone aged X will die within 1 year. So someone aged 47 will die before their 48th birthday. That's the probability. You can see that the first two columns weren't probabilities, these were just numbers, but now QX is a probability also. We won't get into those now. And then PX. Well, PX is not here. It's here, but it's not here. So you must just know that PX is. So then as soon as you have QX, you've got PX. So I'm sure you could assume that PX is kind of the opposite of QX. The probability that someone aged exactly X survives at least 1 year. So they could survive. So the probability of a 47-year-old surviving at least 1 year is 1 minus that number. And then obviously PX, from this we can see that PX plus QX, which should make sense because you either survive or you die. There's like no in between. And then I didn't write EX. Okay, let's talk about EX. Let me just write that down here. So EX is a continuous random variable that's the expected future lifetime of a person aged X. What is that? I didn't write that. Aged X. So we expect someone who is 47 to survive another 28.231 years. And EX is equals to the expected value of what? Expected value of KX. So let's talk about KX. KX is not here, but what KX is it's a discrete random variable. It's the number of years, the Kertate future lifetime of someone. So when we talk about Kertate, we're talking about integers, the whole numbers, how many years someone is expected to live. Maybe you'll survive 1 full year or 2 full years, 3 full years. Not how this EX has some decimals here. We're not working with decimals for KX. So KX, then we'll just write that down. So these two look pretty similar. EX is going to be tabulated here. You'll just take EX from your table. And then let's talk about these two. So very similar to this QX and PX, we've got KPX and KQX. So you could imagine this with an imaginary 1 there. So then it should make sense that KPX is the probability that someone now aged X will survive K years. And then the same for Q. Someone who is aged X now survives K years. What am I saying? So the probability of someone aged X will die within K years. That's the Q. Sorry, a bit of a mishap there. So now we can talk about, I won't get into these last three right now. We'll get into that in a future video, but just to know, this AX with the double dot, that is used to calculate the expected present value of annuities in advance, but where we consider the quotate years and like the probability of someone living at each payment. And then the AX, that is where we use that to calculate the expected present value of a whole life, yes, a whole life insurance benefit for a life aged X. And then PX, we're not working with that one. So then it should just make sense that, you can read down the line, the row, and the column to get your values. I'm sure you can work that out. And there's just a few like formulas here that we can discuss. We've already said this. Okay, so that's how you can calculate. Let's talk about this first one quickly. That should make some intuitive sense. If we think about it, we said that QX is the probability of someone aged X dying within 1 year. So now we're just considering the people that died X over the people who are alive to get that probability. And then we already said that makes sense. And then PX, you can calculate like this, which should also make sense. This is the number of people, no, the probability that someone aged X surviving 1 year. So we just need the people alive at the following year, like X plus 1, over people alive at X, which gives us that probability. Now, KPX, this one is not too difficult to calculate. It's the same kind of method as that. However, KQX is not as quick and easy, but it's not difficult. So it'll be easiest if I do that. So this is the probability of someone aged 40 dying within 3 years. So how we'd calculate this is we would go the people who die at age 40 plus the people who die at age 41 plus people who die at age 42 over the people who were alive at age 40. So that's how you would calculate that. And this was just a bit of an introduction to this notation that we consider with life contingencies, and we'll get into examples in next videos. Thanks.